are weird.
All matter has a wave-like properties, so-called particle wave duality. Particle waves are described in a probabilistic manner. Electron does not whiz around the nucleus. It has probability distribution describing where it might be found, allows for seemingly impossible quantum tunneling. Some properties come in dual packages, cannot know both simultaneously to arbitrary precision, called the Heisenberg uncertainty principle, not simply a matter of measurement precision. Position, momentum, and energy time are example pairs. The act of measurement fundamentally alters the system, called entanglement. Information exchange alters a particle state. Why don't atoms disintegrate in nanoseconds? If electron is orbiting, it's accelerating. Wiggling change emit electromagnetic radiation. Loss of energy would cause prompt decay of orbit. Why don't hot objects emit more ultraviolet light than they do? Classical theory suggested a UV catastrophe leading to obviously nonsensical infinite energy radiating from hot body. Max Planck solved this problem by postulating light quanta.
Why was red light incapable of knocking electrons out of certain materials, no matter how bright? Yet blue light could readily do so even the modest intensities, called the photoelectric effect. Einstein explained in terms of photons and won Nobel Prize. What caused a spectra of atoms to contain discrete lines? It was apparent that only a small set of optical frequencies or wavelengths could be emitted or observed by atoms. Each atom has distinct fingerprint. Light only comes off at very specific wavelengths or frequencies or energies. Note that hydrogen with only one electron and one proton emits several wavelengths. Without quantum mechanics, we could never have designed and built semiconductor devices, computers, cell phones, lasers, CD or DVD players, barcode scanners, surgical applications, nuclear reactors, atomic clocks. Physicists didn't embrace quantum mechanics because it was greatly novel or weird. It is simple that things work so well.
Let's start with photon energy. Light is quantized into packets called photons. Photons have associated frequency. In wavelength, there are three: speed, energy, and the momentum. Energy, higher frequency photons, higher energy, and more damaging. The constant H is Planck's constant, has tiny value of H equals to 6.63 times 10 minus 34 Gs. How come I've never seen a photon? Sunny day, outdoors. 1015 photons per second enter eye, 2 mm pupil. Moonlight night, outdoors. 5 times 1010 photons per second, 6 mm pupil. Moonless night, clear, starry sky. 108 photons per second, 6 mm pupil. Light from dimmest naked eye star, Mach 6.5. 1000 photons per second entering eye. Integration time of eye is about 1/8 second to 100 photon threshold signal level. Quantum wavelength. Every particle or system of particles can be defined in quantum mechanical terms and therefore have wave-like properties. The quantum wavelength of an object is de Broglie equals to photons per momentum, called the de Broglie wavelength. Typical microscopic objects, masses to kilogram, velocities, matter per seconds, momentum equals to 1 kilogram matter per seconds. De Broglie equals 10 minus 34 meters, too small to matter in macro environment. Typical quantum objects, electron, 10 minus 30 kilogram at thermal velocity 105 meter per second to de Broglie equals to 10 minus 8 meter. So de Broglie is 100 times larger than an atom, very relevant to an electron.
The process of measurements involves interaction. This interaction necessarily touches the subject. By touch, we could mean by photo of light. The more precisely we want to know where something is, the harder we have to measure it. So we end up giving it a kick. So we must unavoidably alter the velocity of the particle under study, thus changing its momentum. If the derivative of x is position uncertainty and the derivative of p is the momentum uncertainty, then inevitability. Light emerging from a tiny hole or slit will diverge, diffract. We know its position very well, in at least one dimension. So, we give up knowledge of the momentum in the dimension, thus the spread. Large opening gather position uncertainty result in smaller momentum uncertainty, which translate to less of a spread angle. A small opening, less position uncertainty result in a large momentum uncertainty, which translate to more of a spread angle. Squint and things get fuzzy. Opposite behavior from particle-based pinhole camera. Eye floater. Look at bright, uniform source show tennis pinhole. You can make you'll see slowly moving speck with ring around them. Diffraction ring. Shadow between thumb and forefinger appears to connect before actual touch. A striker street light through windshield point toward center of wiper arc. Diffraction grating formed by microgrooves in windshield from wipers, same as color streak of CD.
The pattern on the screen is an interference pattern characteristic of waves. So light is a wave, not particulate. But repeat the experiment one photon at a time. Over time, the photons only land on the interference peaks, not in the throws. Consider the fact that they also pile up in the middle. Pure ballistic particles would land in one of two spots. Non-intuitive combination of wave-like and particle-like appears to behave in wave-like manner, but with low intensity. See the interference pattern build up out of individual photons, arriving one at a time. How does the photons know about the other slit? Actually, it's impossible to simultaneously observe interference and know which slit the photon came through. Photon sees or feels out both paths simultaneously. Speak of wave part describing probability distribution of where individual photons may land. Mathematical machinery of quantum mechanics is turned to the hydrogen atom. The yield energy levels in exact agreement with the optical spectrum. Emergent picture is one of the probability distribution describing where electrons can be. The energy levels of hydrogen match the observed spectra and fall out of the mathematics of quantum mechanics. Probability distribution are static. Electron is not thought of whiz around atom. It's in a stationary state of probability. Separate functions describe the radial and angular pattern.
These plots describe the directions in which one is likely to find an electron. They are denoted with quantum numbers 1 and m. 1 as a subscript and m as a superscript. The S state is spherically symmetric, equal probability of finding in all directions. The P state can be most likely to find at the poles, in the case of, and exactly the opposite situation in the state. Why do we not see tunneling in our daily lives? Electron always repelled. Electron usually repelled, but will occasionally pop out on the other side of the barrier, even though it does not have enough energy to do classically. If the wall is much thicker than the quantum wavelength, tunneling becomes improbable.